So I will start with a list of the top global challenges that were put together suggested by Richard Smalley, who was a Nobel laureate in chemistry. And it's not surprising when you look at this list that energy and water are the top of the list. We all know it's very, very important. And as you're going to see during my talk, indeed they are interrelated. I would make even more, and I would say that we can define, if you take the top three challenges, we can define a water, energy, food nexus. We talk mostly about the water and energy nexus, but I think food is a major, major problem as much as energy and water, and they are interrelated. So I will coin the term water, energy, food nexus. Now, we all know that there is a water scarcity. We have a global and regional water scarcity. We hear about it in some popular magazines like National Geographic, some books, and even some coin the term water is the new oil. So now, when you think about water, each of us consume millions of liters of water, but you never think about it because this is what we call virtual water. For each apple that you eat, each apple, you need to use 70 liters of water to get this apple. If you take one chicken, as you see here, you will have 4,000 liters just to have one chicken. And again, in the US, they like a lot of hamburgers. It's 2,004 liters for one double hamburger. It can be even worse if you have your leather shoes, and leather shoes can consume up to 17,000 liters per kilogram of leather. So it's a lot of water that we never think about it, but it's there. It's not just the water that you drink. Now, I would say that also related to this water, energy, food nexus, agriculture is a major, major consumer of water, and we usually neglect it. We always think about industry and consumption and safe water, but agriculture is really the main driver of many, many water projects all around the world. This is part of the conversion from PC to Macintosh. So we were supposed to have a nice diagram there that show the percentage of water for agriculture compared to other uses. And as time progresses, it's roughly about 70%. So 70% of the average water consumption is for agriculture. I hope my other beautiful slides will not be damaged. Okay, we'll see some other. But see this conversion from PC to Macintosh. We need to have something more, some of the technologies here to find some way to, or maybe we all should convert to Macintosh. I'm sure Robert will like it. So at least now I convince you, or at least I tell you that there is not enough water. So the question is, how do we increase the available water supply? So of course we can do all the usual things that we always were told. We can do water conservation, repair of infrastructure, improve catchment, but all of these will improve the use of water, and they will not give you more water than what you can get from the hydrological cycle. The only way to get more water than what you can get from the hydrological cycle is to turn to engineering and either desalinate seawater, we have plenty of seawater, or recycle all the wastewaters. And it's done in many, many countries. Singapore, US, Israel, they recycle all their wastewater and they use a lot of desalination. So I will focus only on desalination and talk about some of the technologies. Now, desalination also got a lot of coverage by even high-profile magazines like Science and Nature, the dedicated special issue that talk about water and desalination, and the US National Academies also wrote a big report about desalination, asking if it's really can be a solution to global water scarcity. The main technology nowadays for desalination is reverse osmosis. This is the predominant technology for all the new desalination plants, except some place in the Gulf country that they have still the thermal desalination, which are more energy intensive. So it starts with the intake of water from the sea, goes through some pre-treatment that in principle similar to the way we treat water for drinking water. Then it goes to reverse osmosis that does all the separation of water and salt. This is what most of the energy, as you see from the thickness of the line, most of the electricity comes for this process. And then you have post-treatment to remineralize. And also when you talk about agriculture, the post-treatment that is very, very important is to remove boron and some chloride, because boron is not rejected well by these membranes. And if you have high level of boron, it's not good for many, many crops in agriculture. So boron and chloride need to be removed, and this can be quite costly, also the extra polishing. So just a few words about desalination before getting in depth. It offers seemingly an unlimited steady supplies of water. The ocean is vast. I mean, it will never, you'll have it all the time. Now also, it can produce water without impairing the natural ecosystem. If you take waters from river and lakes, you can affect the ecosystem. You need water from the ecosystem. The ocean, whatever you take, it will be just like one drop it's insignificant. However, and this is what I will emphasize, it's much more energy intensive. It takes about 3 to 4 times more energy to desalinate than the way you treat water. For example, the water that is treated from the river in Rabat and come to your tap water. It's about 3 to 4 times more energy. And there are some environmental concerns about desalination. So I wrote a review article about a year ago that covered some aspect of the seawater desalination. And here I will highlight only a few things and add some more the newer things. And I know Robert told me that he read this article just before I came here, which is good. So I would like now to pose 2 main questions. What is the current energy efficiency of desalination and how it can be improved? Because we really need to understand what's the limit or thermodynamic limit of desalination. Because someone can come to you and tell you, I can do desalination with, 0.1 kilowatt hour per cubic meter, and you believe him or her. It's not the case. There is some limit that you cannot violate, and it's based on thermodynamics. So I would like to show you a diagram of the energy consumption just by the reverse osmosis stage, the one that takes the separate water and salt. Since the reverse osmosis was invented in the late 60s until now. And as you see, the energy consumption achieved a plateau. Now, this was a paper that we've written, but in principle, if you go now, it's about the same. It doesn't change. And note this line, I will describe more the dashed line that you see here. This is the thermodynamic limit that I'm going to describe very soon. Most of the improvements were done here due to a better system, some better energy recovery system, and better membranes. But you reach now a limit that you cannot improve further, and you are very close to what we call the thermodynamic limit of desalination. So this is what I would like to say a few words. From thermodynamic, you can calculate how much energy required to separate water from salt. And you cannot do it with less energy. This is what thermodynamic dictates. This is the limit. So if you take seawater, 35,000 ppm, and you take just 1 drop of water from the seawater, you will need a 0.76 kilowatt hour per cubic meter. Now, most desalination plants work at 50% recovery. It means for each volume of water, you'll get half clean water and half become concentrated. For this, thermodynamics tell you cannot do it less than about 1.1 kilowatt hour per cubic meter. It's impossible. Even if you invent the most, it just cannot. And it's independent of the process. It's just based on thermodynamic. Now, desalination plants require more, and because I will explain it just briefly, in principle, the way you desalinate, you have membrane modules, like a channel with membranes. And you can think about it that the seawater starts here, and the seawater has some kind of osmotic pressure, maybe 27 bar. And as the water coming through the membrane, you squeeze fresh water, the salt inside this membrane element increases. And when you exit the modules, usually it's about 6 meters long, it becomes much more concentrated. So for example, if you start with seawater of 35,000 ppm, 25 bar, at the end of the membrane, you will have a 50 bar. So you cannot operate the reverse osmosis with less pressure than this osmotic pressure of the exit. So this is required, you must apply this pressure, otherwise you will not get water coming out from the membrane, some part here. Remember this part because we will talk about it when we talk how much we can improve desalination. In reality, you apply a little more pressure because of the frictional drag as water flow in the channel. There's some friction and energy losses, so about 10–20%. So this is the way you can operate. If you operate at less pressure, you will not be able to squeeze water through some areas of the membrane. So remember this part. Now, so just summarize the values. So the minimum energy by the reverse osmosis is about 1.1. the best desalination plant that's built nowadays, like the one in Singapore, Spain, and Israel, they do it around 2 kilowatt-hour per cubic meter just for the reverse osmosis stage. However, when you look at the entire consumption of energy by the entire desalination plant, remember there is pre-treatment and post-treatment, is about 3 to 4 kilowatt-hour per cubic meter. So again, the RO, just the reverse osmosis, consume 2 kilowatt-hour per cubic meter. The rest of the plant is about 3 to 4, and the rest of the energy comes from the intake, the pre-treatment, and many times the post-treatment. To remove the boron after the desalination stage, sometimes you need to have another reverse osmosis or even 2 reverse osmosis stages, and otherwise you cannot use the water for agriculture. And this is very important. Desalination become a source for energy, for water for agriculture. Like in Spain, I heard now in Agadir, Morocco, they build desalination plant for agriculture, and the same way in Israel, they use it for agriculture. So now that we know roughly the energy limit of desalination, let's see how we can improve it. So there was a lot of research that said that if we can get better materials, we can make desalination much more energy efficient. And I would like to tackle this problem. One of the hot area of research until recently was what we call high permeability membrane. They promise if you make this membrane with the high permeability, which means the water will go there almost with no resistance, you will have a quantum leap in desalination. You will save a lot of energy, and desalination will be as cheap as making water for treating the river water. And some of the areas of research that they got into are 2. One of them is a line carbon nanotube membrane. They found through simulation that if the water goes through this carbon nanotube, there is no friction because the carbon nanotube are smooth and hydrophobic, and the water goes with no friction. You can get very, very high permeability, and they said that they will, if you use it in desalination, you will have no energy, almost no energy. The same thing with some of the biologists here. Aquaporin, these water channels are known to pass water at very high flow rate, and they suggested to incorporate them into membranes and get this very high permeability membrane so they can reduce the energy of desalination. But I would argue that it's not the case because the flow or the transport of water through the membrane is governed by the thermodynamics, not by the resistance of the membrane, because of what I explained to you here. You must operate with at least this pressure to get any water coming out because of the osmotic pressure of the brine as it accumulates in the membrane channels. And many times, and you need also about 10-20% more to compensate for concentration polarization and frictional drag or pressure drop. And it just happened that the current membranes that we are using nowadays already operate just about this range here. So if you have high permeability membrane, you will not use less pressure. And pressure, the energy is just proportional to the pressure. So you cannot use and desalinate with less of this pressure, and the current membrane already there. So this high permeability membrane, even if, again, they are not even demonstrated that it can desalinate, but even if they will be there, they maybe just reduce the area needed for desalination, the membrane area. But the membrane is only 5% of the total cost of the desalination, so it's not significant. Now, the state of the art in desalination are these thin film composite polyamide membrane. They are very permeable and selective. They retain 99.9% removal of the salt, so retain more of the salt, and get very high water permeability. However, there are many properties that make them prone to fouling, and fouling is the process when you have all these substances in the water that attach to the membrane and affect their performance, like organic matter, particles that accumulate and foul the membrane, so it becomes less permeable. Because they are hydrophobic, they have rough surface, they contain carboxyl group, there are many, and also they are sensitive to chlorine and oxidants. So many of the properties will make them so you will not be able to clean them effectively. They will foul, and once you have fouling of the membrane, you need to increase the pressure so you can squeeze the amount of water that you want. So I would argue that really the improvement, that the high permeability membrane will not improve the energy of desalination because of what I explained. And what you really need is, the key is really to get fouling resistant membrane, because the current membranes are prone to fouling, and also membranes that can tolerate oxidants like chlorine. The current membrane, the polyamide membrane, if you have chlorine, it will degrade and it will not perform well. Now, the membrane companies and scientists try for the last 30 years to find a better membrane than this polyamide chemistry, and they cannot come up to something. Whenever you come something that give you a little more flux, then it cannot reject a lot of salt. So the future, I mean, is really in these materials are to make fouling resistance membrane, and all these nano-type membranes will not reduce the energy of desalination. Now here, again, my original topic title was forward osmosis desalination. And the second question that I posed, are there any technologies that can reduce the energy demand? Like, you know, I talked only about the reverse osmosis technology. The other technology that used in the Gulf country is thermal desalination, that you practically boil the water and condense it and use it again and again. And they are very energy intensive, so they will never be able to compete with desalination. But they were built many, many years ago, and the new plants that are built now almost all around the world are reverse osmosis technologies, including, I mean, the recent one that was built in Agadir, Morocco. So I would like to highlight the process that we sort of working and conceptualize at Yale University. It's called forward osmosis, and see that, again, we are not testing it, that we may be able to use some energy in desalination. So forward osmosis, the principle is that you have a membrane here. If one side you can have seawater, if in the other side you will put a solution of higher concentration, then water will move by osmosis to this side. But again, you don't do much here because you take water from the salt water and put it in another salty solution, although it's a clean solution. And then if you can find some way to recover the fresh water that passed and reuse the salt solution again, it will be a viable process. And this is all the energy. All the energy comes here on the process that you recover the clean water that passed through the membrane and reuse this high concentration salt again. So now we need to come up with some nice or some clever solution for this salt. Otherwise, if you need to use another reverse osmosis to separate here, you will not save energy. So we came up with something that we call thermolytic draw solution. Thermolytic draw solution, these are solutions that if you apply some heat, you can decompose them to something. For example, our solution, we have ammonia and CO2, and I will soon show you how it works. I have some animation. Hopefully it will not be affected by the conversion to Mac. And this draw solution will draw water from the forward osmosis side, and you will need low-grade heat. If you have atmospheric pressure 58 degrees Celsius, you'll be able to break the solution again and use them and get the fresh water. So let's see how it works. As I said, so you apply, if you dissolve ammonia and CO2, you will get ammonium salt. 3 types of ammonium salt, and you can create very, very high osmotic pressure. So this can draw water across the membrane because it has higher osmotic pressure than the seawater. And then, as I indicated, if you apply some heat, you apply low-grade heat or waste heat that otherwise you cannot use it, you can decompose again them to ammonia and CO2, use them again, and stay with the fresh water. Now, if you calculate the energy here, it will be much, much more than reverse osmosis, because you know that thermal processes are not as efficient. However, the cost will be insignificant, because if you use waste heat that otherwise you cannot do anything with it, then it doesn't cost a lot. And the electricity that you need here just for the pumps will be maybe about 0.5 kilowatt hour per cubic meter at most. So much, much less electricity as long as you have this waste heat. So this waste heat can come either from a power plant or in an industrial plant that otherwise will be discharged to the environment. You can also have geothermal. Indeed, this is just a map. I use it for another paper that we are writing, but if you drill a 3.5 kilometer, this will be the thermal, the temperature that you can get there. It's about, most of the United States, about 50 to 100 degrees, which is good enough for this process. And some places here in the Western United States, you can get much higher. Now, the reason, those of you familiar from the US, you see this is the area of Pennsylvania. The reason we did it because this idea of the forward osmosis now, there is a company who commercializes it, and try it on this water that come from shale gas production. When you produce the shale gas water, you get a waste of very high salinity. It can be 5 times more than seawater, and you cannot treat it by reverse osmosis. The only way you can treat it by this kind of processes that need thermal energy. Or you can use just solar thermal, and we had an excellent talk here from Total on solar thermal. Again, this is just in sub-Saharan Africa. I mean, it's plenty. The average there is in the order of 6 to 8 kilowatt hour per meter square per day. And in principle, you can think about this kind of reverse osmosis, forward osmosis. You need more like decentralized and small unit that can supply water just by using thermal energy. So anyway, I would like now to conclude with some recommendations, and these I took directly from the Science Review article that we have written. And these recommendations were mainly, when we were invited to write this article by Science, they wanted us also to say, okay, is it really a sustainable solution, or do you really recommend desalination as the way to solve our global water scarcity? So these are the recommendations that we have made at the end of this relatively scientific article, and I'm quoting them directly. So the first one, although several options currently exist to augment freshwater sources, including the treatment of low-quality local water, water recycling, and water conservation, these options alone will not be enough to meet the need. So you can do all the things, but you still need water in many, many places, including, North Africa and California and the Middle East and so on. Because some environmentalists in the US, they said, no way, it's more like a resistance to nuclear or hydrofracking. No way desalination is too much energy intensive, and you will contaminate the ocean and everyone will die and so on. So now, while seawater desalination must be considered after all other options have been implemented, it should be viewed as a crucial component in the portfolio of water supply options. You need to try all the other options because this one is 3 to 4 times more energy. But if you've done them and you have no water, this should be part of a portfolio for water supply. Indeed, water supply is like energy. You have a portfolio of water supply, and you cannot say that all the water comes from one source. You can have some water that comes from rivers, some groundwater, some desalination, some recycled wastewater, and so on. And lastly, for water-scarce countries that already implement all other measures for freshwater generation, desalination may serve as the only viable means to provide water supply. So we really here recommend, and again, although many scientists and environmentalists object, at least in the United States and some of the Western countries, that if you try all the options, this is a good way. And although it's energy intensive, it's not unusually energy intensive, and it can be used part of the energy portfolio. Now here, I talk mostly with application to the developed world. Again, if it's applied to completely to the developing country, probably not, but anything in between, it's suitable. And indeed, you hear many countries now that build desalination plant, Algeria, Morocco, China, and so on. So it's become really a global solution. So I would like just to thank the former students that did all the work and the funding, and these are some pictures from Yale University. Thank you very much.